So to expand the capabilities of our analysis, we're going to modify the analysis that we just completed by including the effects of rainfall. This will be done by modifying the upper boundary condition, where last time we had a mass flux of 0, and now we're going to include a mass flux that is 2 centimeters per hour of volumetric flux distributed over 1 hour of time. And to do that, I'm going to go up here to variables, and I'm going to calculate first what 2 centimeters per hour is in a mass flux. And so let's do this. Let's make a variable called rain, and 2 centimeters per hour would be 0.02 meters per hour, and then we divide by 3600 to get that in meters per second. So that's the volumetric flux, and then we can do this as rain as let's call it MF, mass flux, and that will be this rain, which is a volumetric flux, multiplied by rho W, which is the density of the water. So we can, that says kilograms per cubic meter for the units, so we can get that into the right units, and this would be good to do as a check if we put some parentheses there, and then in square brackets we'll specify the flux of the rainfall as meters per second. And so if we do that, then you can see we've got the correct units for rainfall as a mass flux. And we can put that here, rain as MF, as the upper boundary condition. So that would be what we would want to do if the rainfall at the coming into the lysimeter was uniform over the entire analysis. Well, if the analysis only lasted for 1 hour, that would be okay. But we'll want to do an analysis for, say, a day to look at what happens when we have the rainfall into the lysimeter, and then after the rainfall that water will redistribute. So in order to do that, we're going to have this boundary condition last for 1 hour as rainfall that's this flux, and then the flux at the top will go to 0. So to make that change, we'll go up here to variables, and we'll go up here to definitions, right click and go to functions and rectangle. So we're going to use a rectangular function to control the rainfall rate. And we're going to start the rainfall at time equals to 1,000 seconds, and then we're going to cut it off an hour later, which would be at time equal 4,600 seconds. And I'm going to smooth the transition, the beginning and the end of the rainfall, over 100 seconds. Let me actually just the default is 0.1. So let me show you what you get with this kind of a specification. Here is the rectangular function. It's 0, and then at 1,000 seconds it goes up to 1, and then at 4,600 seconds it goes back down to 0. And the transition occurs over 0.1 seconds. So we probably want to have a bit of a larger transition, make it a little bit smoother than that. And let me just show you though what happens if we take this size of the transition zone and smoothing and make it 1,000 seconds. You can see then from there to there is 1,000 seconds, and it ramps up now from 0 to 1 over 1,000 seconds. Okay, so it still is a rectangular function, but it's clearly a smooth rectangle. I'm going to go and make it 100, where it's 100. Now it looks, at this scale, looks pretty smooth, but these corners here are curved off. Okay, so this will be what controls the timing of the rainfall. It goes from 0 to 1. So if I take this function and multiply it by the mass flux, then I can turn the rainfall on and turn it off. So I go to the boundary condition here. I've got rain as mass flux, MF, and I'm going to multiply that by this function RECT1, and then I'm going to make it a function of time. Okay, so that name there, right there, is the same as this name right here, where I specified the rectangular function. Okay, so that's how I make the rainfall start and stop. Now, in order to do the simulation, I have to include another study. So I'm going to make this a time-dependent transient study, and I'm going to have the beginning of this study start with initial conditions that were present at the end of the previous study. And to do that, I go here to the study, the time-dependent line, and go up here to user controlled. Well, I've opened up this line here, values of dependent variables, and under initial values of variable solved for, I make it user controlled, and I specify this solution, and I'm going to use the study number 2 and this final time period. Okay, so that should do it. Let's go and try this. Let's run this study. Oh no, I'm sorry, there's one more thing we have to do. We have to specify the time. The default is just 1 second. So let's run this for e to the 5. That's a little over a day. And let's just make it 50 values that we saved from the solution. And now we can run that. Okay, so here's the result. The default is to give us the pressure as a function of distance at the 50 different times. And you can see that we have these two curves that look kind of different than the rest. These are the pressure profiles during the rainfall at the beginning of the simulation. And then the rest of these are the pressure profiles after the rainfall as the pressure redistributes. This is the top of the lysimeter, and the pressure is redistributing basically as the water moves downward. So let's change this and plot the water content. That's called theta. And let's see, if we go down here, there's the liquid volume fraction. That's the volumetric water content. And we use theta for the variable. The dl comes from this. The Richards equation physics is specified right there, and that's called dl for it specifies the physics. So that's why you have the dl out in front of the theta. So let's select that, and we'll replot it by pressing that. And this is what the water content profile looks like, and looks pretty similar to the pressure, but this is kind of hard to see. There are a lot of curves there, so let me just show you a simple way of changing that. Instead of plotting all the times, I'm going to go here to manual, and each one of these curves has a number from 1 to 50. So I'm going to plot the first 5 plots. Let me go back. First 5 plots, I'm going to plot all of them, and then I'm going to start at plot 6 and go to plot 50 and step every 10, and I'll add that, so I get these two ranges for the times when I'm going to plot. Now if I do that, that then gives me this plot for the water content as a function of distance at different times. I'm going to make the lines a little bit thicker here, just so we can see them a little bit better. Okay, so that is the effect of rainfall on the water content profiles. Now we might want to look at these results a little bit differently. We might want to say, well, I have a water content sensor in the lysimeter at a certain depth, and I want to see what the water content is at that depth. So if I want to do something like that, an easy way is to go to data sets, right click, and use cut point 1D, and I'll put in a point at x equals 0.5 meters. I can check where that is by plotting it. There's the point along the domain of the problem, And if I go and make a plot here, if I right click and use, it'll be a 1D plot, and it'll be, I'll plot the point type data, and it'll be the data set will be from that cut point that I just put in. And I'll want to plot water content. That's what the sensor will display, and so dl theta is the water content, and then I'll plot that. Okay, so that's, oh, I know. So this is peculiar. This is not what I was expecting, but here's what happened. Let's go back to this data set. Now, what I did was specify here that the data comes from the 0.5 x equals 0.5 location, but I have 3 data sets that I can choose from: study 1, study 2, study 3. These first 2 were set up to come up with equilibrium conditions, and the study 3 is what I'm interested in. So I need to go here and select study 3, and the data that I have here, this is what the moisture content would look like as a function of time during that first study. So we might be interested in that, but right now we're interested in what happens during study number 3. So there's the result. I changed the study, the data set that it was accessing, and this is the water content now as a function of time. You can see it starts out at 0.28, it jumps up to 0.33 as a result of the rainfall, and then it tails off as that water drains out. So that kind of makes sense, I think. And we might then use data that we had from measurements in a real lysimeter to help calibrate the model. That might be one approach that we could use. Some other things that we might be interested in is the inflow, comparing the inflow and outflow rates in this experiment. And so we could do that by making another plot. I'm going to do a 1D plot, and this will be a point plot, and we'll just look at what the flow rate is at, I think we can just plot the flow rate at the 2 ends, and the flow, we'll plot it as a flux, a volumetric flux, which is dl, is called the Darcy velocity. So if we plot that variable and make a plot of that, and we need to do the same thing. We need to check, always need to check and make sure that we're plotting the data set that we want. So this is going to be data set number 3. Okay, so there we have the inflow and outflow, and I'm going to make these lines a little bit thicker. If I go to coloring and style, I can do that just to be easier to see. So here the green shows the inflow rate. This is the rainfall. You can see it stepping up and then stepping down abruptly. And the blue is the outflow. And so you can see that there's really no outflow at the time the rainfall stops, but that wetting front moves downwards, and the flow starts here and starts to pick up and reaches a peak here after this many seconds, and then slowly tails off. And you can see after the end of a day you still have some outflow. So that, I think, makes sense intuitively, and gives us, actually this would be another data set that we could compare to if we had a way to measure the outflow rate as a function of time. Now we might also be interested in characterizing the average water content in the lysimeter at any given time. So we can do that by going here to derive values, and let's do an average over a line. So if we do a line average and we select that line and we select here dl theta, this would be the water content that we average over this line as a function of time. And we can then evaluate this, and this is going to make a tabular output right here. And actually we've got to go and check again. I keep making this mistake, but it's good because it'll make sure that you recognize this, because we've got these three solutions, so we're interested in solution number 3 for this analysis. And if I press evaluate again, what I get now is this is the average water content for solution number 1, and this is for solution number 3. And if we don't want any of that, we can just hit the garbage can and erase it. So I'm going to run the evaluation again, and here's the analysis for the average water content as a function of time in the analysis. And then this would be good. We could import or export this and use it for various applications, but we also just might want to plot it up, so we can hit the table graph right here. And here's a plot of the average water content that's in the core as a function of time. And so this would be something that would be useful if we had, particularly if we had a way of measuring the average water content over the core. And we might be able to do that, but something that we certainly could do would be to evaluate or measure the weight of the core as a function of time. We could do this with load cells. And so if we take the average water content, we can convert that into a load or a weight, and this curve here would be then a plot of the weight or the signal that we would expect to see in the load cell.